Okay, I want to talk a little more about the force of gravity. And the force of gravity is sometimes called the weight. Force of gravity. And it's the force that's put on an object because of its attraction to the center of the earth, to the mass of the earth. And it turns out two masses will always attract. And we need to talk a little bit about the difference between mass and weight, because this is one of the most confused concepts in physics. Mass is how much stuff. How much stuff is one way of saying it. And we have a special term. Well, we'll also say how hard it is to accelerate. Okay? So I'm going to take this little eraser, and it's real easy for me to speed it up or slow it down. Okay? I'm going to do the same thing with this. Oh, it's harder for me to speed it up and slow it down. Okay? It's got more stuff. It's got more mass. Okay? This is measured in kilograms, and this is what measured in weight is measured in newtons. And yes, absolutely, this has a lot less weight. Earth is pulling down less strongly than this. But what's really important is doesn't depend on environment. Mass exists even far away from any planets. Doesn't depend on location. Okay? So this is a 1 kilogram mass. 1 kilogram mass. Okay? This, I can feel how hard it is. I don't have to pick it up. I can tell how much stuff is in there. I can tell how hard it is to accelerate. Well, if I was on a space station, and there's a table there, to move it back and forth would take the exact same amount of work. The example that I use a lot is something that has a lot of mass is a space station, okay? If you had a space station on rollers down here on Earth, and you tried to push it back and forth, you're going to be the person who moves back and forth. Very hard. This is a huge thing, right? If you're up in outer space and you grab onto the side of the space station and you try to do this, same thing's going to happen. You're going to move back and forth. It's very hard to move because it has so much mass, so many kilograms. But up in space, things have a very much smaller weight. Okay, it never actually ends up being zero. You could be almost infinitely far away. You could be very, very far away from the Earth, and it will still exert a pull on this, but it will not exert the same amount of pull that it does here near the Earth's surface. Farther you get away, the less pull the Earth has. So weight depends on its force of gravity. Force due to gravity, I'll just say, due to gravitation. Okay, so weight's a little more complex. It involves an interaction. And it definitely depends on location. Okay. Now, in this class, in AP Physics and Intensified Physics, we're always going to be doing labs and things near the Earth's surface. Most of the problems we set up are near the Earth's surface. So unless we talk about it, so many thousands of kilometers away from the Earth's surface, the weight will be constant. Okay. The mass is constant everywhere. Weight really depends on how close you are to a planet, for example. Okay, now, there's one really nice thing about it. Now, the relationship between these things. The force of gravity, and I wish I'd kind of had these on opposite sides. Force of gravity, or the weight, let's be consistent, capital G, is equal to the mass times the field strength of the planet, we'll say. Okay, so when you're near a planet, you might recognize this G. That G near the Earth's surface is 9.81. And I'm going to use a different unit. We always had it as the acceleration due to gravity, free fall acceleration, meters per second squared. But unit-wise, remember a Newton is a kilogram meters per second squared. So this is the same as newtons per kilogram. I like this unit for G. Think of it this way. If you have so many kilograms, and you multiply it by 9.81 newtons per kilogram, the kilograms will cancel, and you have newtons, which is a force. This looks, wait a minute, if I want to find the weight of this, it's not accelerating, so it's a little misleading. I like this a whole lot better. It's a ratio. It's how many newtons it's pulled on by the Earth's gravitational field for every kilogram of mass that's in there. What's really, really nice about this is really close to 10 newtons per kilogram. That means every kilogram of mass is pulled with a force of 10 newtons near the Earth's surface. So 1 kilogram mass, 10, and in AP problems, in class, you can always use 10 for this. You don't have to use 9.81. In labs, I'm generally going to want you to use 9.81, so it's a little more exact. But on tests and quizzes, you can always use 10 in my class. Okay. Online assignments, very frequently, they'll want the actual 9.81, but they should tell you. So this is pulled by 1 times 10. 1 kilogram times 10 newtons per kilogram is 10 newtons, is the force of gravity. This is so, we're so used to this and we're so used to using this that sometimes we don't even write force of gravity. We sometimes just write mg. You'll see on a free body diagram, you're allowed to write mg. And I do that almost exclusively. It is so easy. This is so easy. If you can keep apart the concept of mass and weight, then anything. Oh, this, by the way, has 0.05 kilograms of mass. M equals 0.05 kilograms. What is the weight? That's right, you multiply it by 10. So the weight, the force of gravity is 0.05 times 10 equals 0.5. Okay, newtons. I have a mass of 80 kilograms. My weight is 800 newtons. So understanding the difference, really, really important. That's a place that a lot of people screw up. Understanding how on Earth we find the force of gravity given the mass and g. We can work it in any different ways, any number of different ways. So for example, this board has a weight of 20 newtons. Well, 20 newtons divided by 10. 20 newtons divided by 10 would give me 2 kilograms. And by the way, to get a feel for this, this is like the mass of a book, of just an average book. 1 kilogram. It weighs 2.2 pounds near Earth. So 2.2 pounds is very close to 10 newtons. Think of a book. A book would be weight of 10 newtons, mass of 1 kilogram.